The assumption, everyone agreed on that was completely wrong. For centuries, no one questioned it. It felt too obvious to doubt. Reality itself seemed to confirm it every day. That assumption was that the universe behaves the same no matter where you are or how you move. That the rules of nature sit quietly in the background, fixed and impartial, waiting to be discovered. This belief shaped everything from early astronomy to modern engineering. It made the universe feel stable, predictable, and fair. It provided a foundation that seemed unshakable, a bedrock upon which entire scientific disciplines could be built with confidence. The assumption felt less like a choice and more like an unavoidable truth, something so self-evident that challenging it would seem absurd. To see why this matters today, we have to return to a time when agreement felt like proof, when repeated success reinforced confidence. Motion could be measured, time could be shared, space felt uniform. Experiments worked the same way in every lab, and that consistency built trust. The universe appeared cooperative. Scientists across continents could compare their findings and discover that nature followed the same patterns regardless of location. This reproducibility became the hallmark of scientific legitimacy. If a phenomenon could be observed consistently, it was considered real. If predictions matched outcomes repeatedly, the underlying theory was accepted as valid. The more experiments confirmed expectations, the stronger the assumption became. It seemed only logical that if the universe presented itself identically to everyone, then there must be a single, objective reality underlying all observations. But hidden inside that agreement was a silent shortcut. Scientists assumed that if results matched expectations, the underlying assumption must be correct. No one stopped to ask whether consistency meant truth or merely convenience. The assumption had become invisible precisely because it worked so well for so long. It explained planetary motion, terrestrial mechanics, and everyday experience with remarkable accuracy. Why question something that had proven itself over and over? The shortcut was subtle, equating predictive success with fundamental correctness. Just because a model works does not necessarily mean its foundational assumptions reflect the deepest nature of reality. Yet this distinction was rarely made because practical success felt like theoretical validation. The first cracks appeared not as failures, but as tiny mismatches. Measurements that agreed almost perfectly, but not quite. Effects so small they could be dismissed as error. Yet they appeared again and again, refusing to disappear. These were not the kind of dramatic contradictions that force immediate reconsideration. They were whispers, not shouts. Anomalies that could be rationalized, minimized, or set aside for future investigation. But their persistence was troubling to those paying close attention. A true error would be random, scattered, inconsistent. These discrepancies had a pattern, a stubborn regularity that suggested something systematic was being overlooked. These anomalies hinted at something uncomfortable, that the universe might be consistent, but not in the way everyone agreed on, that the rules were holding, but the interpretation was not. Perhaps the universe was speaking in a language that had been misunderstood. Perhaps the framework through which observations were being filtered was distorting the message. The possibility that consistency could exist without the assumed form of universality was deeply unsettling. It meant that decades of accumulated knowledge might need reinterpretation, that the conceptual scaffolding holding up modern science might require fundamental modification. What everyone agreed on was about to collapse, not because the universe changed, but because someone finally questioned the assumption no one thought a challenge. The collapse would not come from new data alone, but from a willingness to reconsider what that data actually meant. It required intellectual courage to suggest that perhaps the entire scientific community had been operating under a flawed premise, no matter how useful that premise had been. At first, these discrepancies felt insignificant, fractions of a percent, tiny timing errors, slight shifts that lived comfortably inside experimental uncertainty. Nothing dramatic enough to threaten a worldview built on centuries of success. Experimentalists could always find reasons to doubt their instruments before doubting their theories. Measurement precision had limits, environmental factors introduced noise, and human error was always a possibility. The anomalies were small enough to be rationalized away without much difficulty. They did not demand attention because they did not disrupt the overall picture. Most scientists went about their work without worrying about these minor inconsistencies, trusting that future refinements would resolve them. So they were ignored or explained away. Instruments were blamed. Conditions were adjusted. Data was smoothed. The assumption remained untouched, protected by its usefulness. There was no conspiracy here, no willful blindness, just a natural human tendency to preserve frameworks that have proven valuable. The assumption had earned a protected status through centuries of reliable service. Abandoning it would mean abandoning a worldview, and that is never done lightly. Scientists are trained to be conservative with foundational principles, to exhaust all other explanations before questioning the bedrock. And for a long time, there seemed to be plenty of other explanations available. But as experiments became more refined, the anomalies grew sharper. They appeared in different places, under different conditions, measured by different people. The same quiet disagreement surfaced again and again. Reality was obeying the rules, but not the interpretation of them. Improved instrumentation removed the convenient excuse of measurement error. Better controls eliminated environmental factors. Increased precision turned whispers into clear signals. The pattern was undeniable now. Different observers, using different methods in different locations, were finding the same type of mismatch. The anomalies were not artifacts of poor technique. They were genuine features of nature that the prevailing framework could not accommodate. The conflict deepened when scientists realized the issue was not what was being measured, but how. Measurements depended on motion, on perspective, on the state of the observer. What was thought to be universal was quietly conditional. This was a profound and disturbing revelation. It meant that the act of observation itself was entangled with what was being observed in ways that had never been properly acknowledged. The observer was not a passive recipient of information from an independent reality. They were an active participant whose state influenced the results. Time measurements varied depending on relative motion. Spatial intervals changed based on velocity. Events that appeared simultaneous to one observer occurred in sequence to another. This realization was dangerous, because if results depended on who was measuring them, then there was no single, absolute description of events. Agreement was no longer guaranteed. Two observers could be equally correct and still disagree. This threatened the very notion of objective reality that science had been built upon. How could there be scientific progress if different observers could not even agree on basic facts about when and where things happened? The implications were philosophically destabilizing, yet the mathematics and the measurements both pointed in the same direction. Nature was not cooperating with human intuitions about how reality should work. This was not philosophical speculation. It was forced by data. Experiments demanded a new explanation, one that did not rely on sheer assumptions about time, space, or motion. The universe was still consistent, but it was consistent in a more subtle way. The consistency was mathematical, not experiential. The laws governing natural phenomena remained universal, but their manifestation depended on reference frames. What was conserved was not the measurements themselves, but the relationships between measurements. The challenge was to find a new framework that preserved the universality of physical laws while accommodating the relativity of observations. By this point, the assumption was no longer safe. It had become a liability. What everyone agreed on was blocking progress, and the deeper physics looked, the clearer it became. The universe was not required to honor consensus. No amount of wishful thinking or attachment to comfortable ideas could change what experiments were revealing. The data was not going to adjust itself to fit human preferences. Either the framework had to change or science would stagnate, unable to explain an expanding body of observations that refused to fit the old paradigm. The assumption had to be abandoned, not because it was useless, but because it was incomplete, and that incompleteness was now preventing deeper understanding. Something fundamental was about to give way, not a law, but an expectation. And once that expectation broke, nothing would look the same again. The coming revolution would not overthrow the empirical successes of the past, but it would recontextualize them, showing that they were approximations valid under limited conditions rather than absolute truths valid everywhere and always. The conflict reached its peak when scientists stopped trying to fix the data and started questioning the assumption itself. What if the universe was not the same from every perspective in the way everyone believed? What if consistency did not mean sameness? This shift in approach marked a turning point. Instead of forcing observations to conform to theory, perhaps theory needed to conform to observations. The question became not, how can we explain away these discrepancies, but what is the universe actually telling us through these discrepancies? This required a fundamental change in mindset, a willingness to let nature speak on its own terms rather than insisting it speak in a familiar language. This idea felt heretical. The assumption was woven into every equation, every experiment, every explanation. Removing it meant rebuilding physics from the ground up, but the evidence left no alternative. Measurements of time disagreed. Lengths depended on motion. Events that seemed simultaneous refused to stay aligned. The mathematical structure of physics would need revision. Textbooks would need rewriting. Intuitions cultivated over years would need to be set aside. Yet science had faced such upheavals before and emerged stronger. The willingness to overturn cherished beliefs in the face of contrary evidence was precisely what distinguished science from dogma. The build-up revealed a shocking pattern. The laws of physics were identical everywhere, but their outcomes were not. The rules held firm, yet the results shifted with perspective. Reality was consistent, but not absolute. This distinction was crucial. Universality did not mean uniformity of experience. The same laws could produce different observations depending on the observer's state of motion. What remained invariant were deeper mathematical structures, relationships between quantities that held regardless of perspective. These invariants were the true universals, not the raw measurements themselves. This reframed the problem entirely. The universe was not breaking its own rules. Humans were misinterpreting what those rules meant. Nature did not promise a single shared viewpoint. It promised coherence across all viewpoints. The challenge was to find a mathematical framework that expressed this coherence, that showed how different perspectives were related to each other in a consistent way. The universe was not contradicting itself. Human expectations were contradicting the universe. Once this was understood, the path forward became clearer, even if it remained difficult. Emotionally, this was destabilizing. Certainty dissolved. Objectivity became conditional. There was no longer one correct description of events, only descriptions that agreed within their own frames. This felt like a loss, a descent into relativism where all perspectives were equally valid and truth became subjective. But that was a misunderstanding. The new framework was not abandoning objectivity. It was refining what objectivity meant. Truth was not subjective, but it was relational. Different observers could have different experiences, while all being objectively correct, because their experiences were connected by precise mathematical transformations. Objectivity was preserved at a deeper level. By this point, the assumption had fully collapsed. What everyone agreed on was not wrong, because it was careless. It was wrong because it was incomplete, and replacing it required a new way of thinking about space, time, and reality itself. The old assumption worked magnificently within its domain of applicability, but that domain had limits. Those limits became visible only when experiments pushed into new regimes where velocities approached fundamental speeds or measurements achieved unprecedented precision. The assumption was not discarded but transcended, incorporated into a larger framework as a special case valid under restricted conditions. The climax of this story is a realization that permanently reshaped how reality is understood. The assumption everyone agreed on was not that the universe had rules. It was that those rules produced the same reality for everyone. This distinction matters profoundly. The existence of natural laws was never in doubt. What was in doubt was the nature of the reality those laws described. The assumption had conflated lawfulness with uniformity of experience, treating them as if they necessarily implied each other. But nature had separated them. Physical laws could be universal, while experiences remained frame-dependent. Once that belief collapsed, a deeper truth emerged. The laws of physics are universal, but experiences are not. Space and time do not sit still in the background. They respond to motion, energy, and perspective. Reality remains consistent, but only when those differences are accounted for. Space and time were not the fixed stage on which events unfolded. They were themselves dynamic aspects of physical reality, woven together into a unified structure that bent and flexed in response to matter and energy. This was not metaphor but mathematical reality, confirmed by countless experiments and technological applications. This was not a loss of objectivity. It was a refinement of it. Objectivity no longer meant forcing the universe into a single description. It meant understanding how different perspectives fit together without contradiction. Truth was no longer singular. It was relational. Objectivity became about finding the invariant structures that persisted across all reference frames, the deep patterns that remained unchanged even as surface appearances varied. This was a more sophisticated notion of truth, one that acknowledged the observer's role while preserving the independence of physical law. It was objectivity without naive realism, truth without absolutism. This shift changed everything. It explained why time stretches and shrinks, why distances depend on motion, why observers can disagree without error. The universe did not abandon order. It revealed a deeper one. Phenomena that had seemed paradoxical or impossible suddenly made sense within the new framework. Effects that appeared only at extreme velocities or in strong gravitational fields found natural explanations. The universe was not arbitrary or capricious. It was following precise mathematical rules that human intuition, shaped by everyday experience, had simply failed to anticipate. Technology quietly depends on this insight every day. Satellites adjust their clocks. Navigation systems correct for perspective. High-speed particles obey rules that only make sense once the assumption is gone. The modern world runs on a universe that does not behave the way everyone once agreed it should. Without accounting for these perspective-dependent effects, global positioning would fail, telecommunications would drift out of sync, and particle accelerators would produce inexplicable results. The practical success of these technologies provides daily confirmation that the new framework captures something real about nature, that it is not merely theoretical abstraction, but empirically grounded truth. More importantly, it reshaped humility. Consensus is not proof. Intuition is not authority. The universe does not reward agreement. It rewards accuracy. This lesson extends beyond physics. It serves as a reminder that truth is discovered, not voted upon. That nature is indifferent to human preferences, comfortable assumptions, and cherished beliefs. That progress often requires abandoning what feels obvious in favor of what actually works. Scientific humility means remaining open to the possibility that our deepest convictions might be incomplete, that there are always further layers of reality waiting to be uncovered by those brave enough to question what seems unquestionable. The assumption everyone agreed on failed not because it was foolish, but because it was comfortable. And reality has never promised comfort. It promises consistency, even when that consistency forces us to let go of what feels obvious. Comfort comes from familiarity, from ideas that align with everyday experience and common sense. But the universe operates on scales and in regimes that everyday experience never encounters. Expecting nature conform to human intuitions developed for survival on Earth's surface is a form of hubris. Reality owes us nothing. It simply is what it is. And our task is to discover its nature rather than prescribe what we think it should be. Understanding did not arrive by defending agreement. It arrived by questioning it. And once that door was opened, physics never looked back. The lesson was learned, even if it must be relearned by each generation. Progress comes not from protecting established ideas, but from testing them, from maintaining the courage to follow evidence wherever it leads, even when it leads away from comfort and towards strangeness. The universe is under no obligation to make sense to us. We are obligated to make sense of the universe. And that requires the humility to admit when we have been wrong, the flexibility to change our minds, and the persistence to build new understanding from the ruins of old certainty. The